about the ratio test and root, the ratio and root tests. Okay, this is section 10.7, is it? Yes, I think 10.7, yeah, the book. So these are theorems, which I'm just going to state without proving. Theorem, this is the ratio test. Now, let EK be an infinite series. An infinite series with positive terms. Okay, and then let R be the limit as k goes to infinity of AK plus 1 over AK. AK plus 1 over AK. Alright? If R is between 0 and 1, then the series converges. Alright? If R is greater than 1, the series diverges. If R is equal to 1, the result is inconclusive. Okay. One thing I'm going to say is that the ratio test works best, or one good time to use the ratio test is when you have factorial, right? So let's do a little review of factorial in green. So remember that if you have, I'm just going to use an example instead of making it so abstract. So assuming we have 5 factorial, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, etc. Right? So 4 factorial, so copy this. Right? 4 factorial is 4 times 3 times 2 times 1, right? 3 factorial is 3 times 2 times 1, etc. So now look at this. Since we know what 4 factorial is, this looks like 4 factorial right here. Okay, this looks like 3 factorial. So this would be maybe 2 factorial, actually 2 factorial. So 4 factorial can be written as 5 factorial can be written as 5 times 4 factorial. So that means 4 factorial can be written as 4 times 3 factorial, and so forth. But what I'm pointing to is that in general, k plus 1 factorial can be written as k plus 1 times k factorial. How many of you have seen the sign factorial before, the notation or the concept? How many of you have studied it before? Okay, good. Now, let's do an example we want to determine our convergence. All right, so the first one, we're going k from 1 to infinity of h to the power of k over k factorial. All right, so we have our ak here is h to the power of k over k factorial, so that ak plus 1 is just to replace all the k's with k plus 1. Okay, so now let's apply the ratio test. For the ratio test, the first thing we need to compute, so let's apply ratio test. The first thing we need to compute is the limit as k goes to infinity of ak plus 1 over ak. So this is the limit as k goes to infinity of h to the power of k plus 1 over k plus 1 factorial, right, divided by h to the power of k over k factorial. Okay, so this is the same thing as limit as k goes to infinity of h to the power of k plus 1 over k plus 1 factorial times k factorial over h to the power of k. Now, I'm going to break this down a little bit as k goes to infinity of h to the power of k times 8, because that will give us h to the power of k times h to the power of 1, which is h to the power of k plus 1 over k. K plus 1 factorial, we know that is k plus 1 times k factorial times k factorial over h to the power of k. So we can have a little cancellation party here. This and this will cancel out. This and this will cancel out. All right, so this leaves us with the limit as k goes to infinity of h over k plus 1. As k goes to infinity, this limit is 0. Right. Okay. So we apply the ratio test. To really well apply the ratio test, you have to understand what factorial is. So now let's go to our statement of the ratio test. When r is less than or equal to 0, and sorry, less than or equal to 1 but greater than or equal to 0, less than 1 but greater than or equal to 0, then we conclude that our series converges. So this means that our series must converge. Okay. All right. Any question? Does anybody have any question? Okay. So that's one example there. Let's state another theorem. We're going to state the root test. The root test is very similar to the ratio test. Okay, so I'll paste it here. I'm going to change a few things. So this is the root test. We're going to say, instead of positive terms, we're going to say non-negative terms. and then we're going to say let maybe rho in this case be the limit square root of ak. Okay, so it's the same thing, but you're just changing this. Instead of r equals limit as k goes to infinity of ak plus 1 over ak, you define rho this way. All right, so I'm going to do an example. All right, so the root test works better. It works better when you have something to the power of k, but you don't have factorial. All right, let me do an example. So how about this series? We have 4k squared. Let's do 4k squared minus 3 over 7k squared plus 6 to the power of k. When you have like a kind of a complicated fraction or a complex fraction, and then you're raising it to some power, the root test usually comes in handy during this period. So let's look at root test. So we want to take the limit as k goes to infinity. This is our ak of ak. K, this is not square root. I have to be very, very careful. Sorry about that. I wrote square root, but this should be kth root. The kth root of ak. All right. So we need to use the kth root of our ak. So this will be limit as k goes to infinity of the kth root of 4k squared minus 3 over 7k squared plus 6 all to the power of k. So if you take the kth root of something to the power of k, you're just left with that something. Limit as k goes to infinity of 4k squared minus 3 over 7k squared plus 6. This limit, does anybody know the answer to this limit? Anybody? 4. So it's 4 over 7. 4 over 7 is good. All right, so and this is less than 1. So this converges. If it were greater than 1, then it diverges. So I gave you 2 examples that involves convergence. In the quiz, I'm going to give you examples that involves divergence. Questions? Okay, let's look at all the tests we've done so far. Okay, so we did the geometric series test, the p-series test, divergence test, integral test. Okay, we did a ratio test today. We did the root test today, and then there's a comparison test. We looked at it, but it's in the video. Limit comparison test and alternating series test. my suggestion is that this is, whenever you're given a series, you should know your geometric series. If it's a geometric series, then you can easily kill it. You can easily know how to deal with it, right? If it's a P series, you have a way of dealing with it. If it's neither a geometric nor a P series, think of it, try using divergence test. Okay? If it's not, if the divergence test doesn't work because it's very easy, think of the integral test, right? The ratio test or the root test. This, and that. Usually, the ratio test is easier, then the root test might be easier than the integral test. So these three are in one category. If they don't work, then think of the limit comparison the comparison test or the limit comparison test. Okay. And then, if it's an alternating series, use the alternating series test. I know I had just said that the integral test, ratio test, and the root test are in the same category. I'm actually going to throw in the comparison test in there. Comparison test, root test, ratio test, and integral test. Unfortunately, you can't just easily distinguish them. I think the comparison test might actually be the easiest, because if you can compare the terms in your limit, in your series, to the terms in a P series, it makes it easier to deal with. Okay, so now I'm just going to look at a bunch of series, and we kind of discuss them, not necessarily solve them. We discuss what we can use to solve them. My stuff is crashing. Give me a minute. Okay. All right, let's look at, stop recording.